Beginning the 2008 E&M free response question number 2, let's go ahead and begin. We want to calculate, so we're going to close the switch and immediately after we close the switch we're going to have a 50 ohm resistor, and we want to calculate the voltage across, basically the resistor, the inductor, and the capacitor as this circuit is connected. So let's go ahead and do that now. So and we want the resistor, and we want the voltage across the resistor R2. So at time equals 0, if we put a 50 ohm resistor here, in part I, or A1, we put a 50 ohm resistor there. Let's just be clear on what happens. We will have a situation where what we can do is we can get the total resistance. Since we have a 50 ohm resistor here, working through, what I will do is I will actually call this resistance R4, and I'll say that it's equal to 50 ohms. So what that does is that gets us R34 equal to 150. Now, since R2 is in parallel with the combination R34, I can say that R234 equals 1 over 150 plus 1 over 300 to the negative 1. And when we actually put that on our calculator and figure it out, that's going to be 2 over 300 plus 1 over 300, which is 3 over 300 to the negative 1. That's going to give us 100 ohms of resistance for the combination. So what we're saying is this total combination here in A equals 100 ohms. So we have 200 ohms in series with this 100 ohm combination. So that's going to give us 5 amps of current coming out of the battery in part A. So just to kind of be careful on that, let me just go ahead and just say that right here, that when we combine this in part AI, the resistance 234 equals 1. Sorry, let me just highlight that one more time. So in part A, numeral 1, in that part, we're getting R234 equal to 100 ohms when we combine it. So what that means is that our total resistance is R1 through 4, or R total, is going to be 300 ohms. Using that fact, we can then say that the current coming out of the battery is 1500 over 300, which is going to be 5 amps worth of current coming out of the battery. So what we can say then is we can actually sort of go and sort of expand out the circuit again, meaning we can write it as the original circuit without thinking about the combination of resistors and use Kirchhoff's rules right here. So now what I'm going to say for this loop is I'm going to say 1500 minus the voltage across resistor 1 minus the voltage across resistor 2 equals 0. So that tells me that 1500 minus 200 times 5 minus the voltage across resistor 2 equals 0. So I'm getting 500 volts as the voltage across resistor 2 for AI. Next, if we have an inductor right here, the inductor acts like a break in the circuit. So what that means is for this part right here, letter A, 2, this acts like a break. And so that means the current doesn't even see this branch. It starts at the 1500 battery, goes to the 200, goes to the 300 ohm resistor. So then what ends up happening is that we're going to get a current coming out of the battery, which we'll calculate like this. We have R12 equal to 500. So that means the current coming out of the battery in A2 is going to be 1500 over 500, which is 3 amps. And so to get the voltage across the resistor, we can take 3 times 300. So V2 is going to be I times R, which is 3 times 300, which is going to be 900 volts. Lastly, if we have an initially uncharged capacitor, what we can say is that we have a situation kind of like the first situation where instead of a 50 ohm resistor, we have a wire here. So now we have a 300 and a 100 in parallel, and that combination is in series with R1. So what we can say is, let's get the total current coming out of the battery. To do that, we're going to get the combination resistance. So this will be A part 3. And what we'll do is we'll combine the 300 and the 100 in parallel. So R23 is going to be 1 over 300 plus 1 over 100 to the negative 1. So that'll be 300 divided by 4, which I believe is 75. Yes, so I'm getting that R23 is a 75 ohm resistor. And so what that tells me is that R123 is going to equal 275 ohms. Let's use that to get the total current coming out of the battery. So that's going to be 1500 divided by 275. So we're getting a total current, 1500 divided by 275, of 5.45 amps. So here's what that tells us. That tells us that we have, again, we'll do the same Kirchhoff's rule that we did in part A, 1. So we're going to say then that, let me just clean this up just a little bit. We're going to say that 1500 volts minus 5.45 times 200 minus V across R2 equals 0. And so what we're getting for V2 then is going to be 1500 minus 5.45 times 200. That's getting us 410 volts. So the answer to A1 is 500, the answer to A2 is 900, and the answer to A3 is 410 volts. Now we're saying that the switch gets close to time equals 0, and we're going to sketch the current across the 100 ohm resistor as a function of time. So, with that in mind, in the first case with the 50 ohm resistor, we're going to have basically a steady current that never changes in the first case. In the second case, we're going to end up getting a situation where we at first have no current, and then we get up to some final level of current, which I can graph like this. So this is with the L, this is with the R, and then with the capacitor, we start off with a current, and then it eventually dies off to 0. So those are the three cases that we end up getting. Now, we can be a little bit more careful about whether that final occurrence is bigger or less than what the r is here, but we're just going for the shapes of the graph, so that's all we care about for B. All right, so that is it for problem number 4.